All right, let's practice using the surface area formula. Nothing fancy here, just trying to set up the double integral. In this problem, they're asking us to estimate, so either the integral is super annoying or not, computable, so we're going to just complete it in Wolfram alpha. All right, the function we're looking at is this 1 over 1 plus x squared plus y squared. I'm sketching the region, which is a disk, and I think polar coordinates will probably be the best to set it up once we get the double integral written. So I'm quickly expressing that circle in polar coordinates, and now let me inspect the surface, get some partial derivatives so that I can fill out the surface area formula. The partial with respect to x, here I'm just very carefully holding y as constant and integrating with respect to x, as we always do when we're taking partial derivatives. And I'm using chain rule and getting the following answer. dz dy is going to go exactly the same way, of course, because y and x play sort of the same role in this function. And once I have my partial derivatives, in order to fill out the integrand of the formula, I just square them both, add them together, and add 1, and put that all under a square root. So I'm just working out all that algebra over here. Try and stay organized when you're doing your own work. That's going to help me grade, and it's also going to help you, so that you know where you're at in the problem and so on. Okay, so this is the contents of the radical expression in the integral. So I'm ready to set up my integral. I'm going to do polar coordinates because I'm integrating over a circle. That makes most sense. So I put the polar coordinates where they belong on the integral signs, and then I'm going to convert the integrand into polar coordinates. I've got lots of x squared plus y squareds, so those become r squareds. And remember, with a polar integral, your dA unit is r, dr, d theta. Wolfram alpha does double integrals for you. So I typed in the integrand and the limits. I confirm that that's the integral that it's computing, and it's about 3.6, I guess, as an answer. So I'm just going to go ahead and copy that whole image over here, and that's my answer. Obviously, you're not going to well, I was going to say you're not going to do this on tests, but since you're working from home, maybe you can do this on tests now. Anyway, let's do another one. This integral we're going to compute by hand. I want to find the area of a portion of a sphere. So I'm going to go ahead and complete the square on this thing so I can get a better idea about how it's positioned. I see that its center is 0, 0, 2, and its radius is 2. So here's a drawing of the sphere, but I don't want the whole sphere. I just want the point that's lying inside of this paraboloid. So I'm getting my paraboloid drawn as well. I'm not entirely sure of the arrangement of these two things, so I'm going to pop over to GeoGebra and see, okay, that paraboloid cuts a cap of the sphere off. So I'm going to algebraically determine, over what region in the domain does that cap lie. So I'm drawing the cap here, and then I'll do some algebra off to the side, which just amounts to basically setting those two surfaces equal to each other to get, the x and y domain that's appropriate here, this D circle in the xy plane. So I see that the paraboloid is described by z equals x squared plus y squared, and there's a term of x squared plus y squared in the sphere equation as well. I can also see it in the original sphere equation that didn't have the square completed. So replacing x squared plus y squared with z, I get the following equation, and that tells me the z values of intersection. So the paraboloid intersects the sphere at z equals 0, and it also intersects at the level z equals 3. Let me get that in terms of x and y. So if I carry 3 back to the paraboloid equation, I get that 3 equals x squared plus y squared. That's the equation of a circle. So I understand that to be this D disk down in the xy plane, x squared plus y squared less than or equal to 3. As before, I'm going to set that up in polar coordinates when I set up my double integral for the surface area. Okay, so I'm reminding you the surface area formula, just as we used a second ago. You take the partials, square them, add them together, and add 1, and integrate that dA. Okay, so let's go ahead and express everything in terms of polar coordinates now. I see that the sphere, which is the surface that I'm trying to find the surface area of, it's given to me implicitly, so I can use implicit differentiation to compute both of the partials. So I'm just differentiating both sides with respect to x, as I normally would do with implicit differentiation, and I get this expression for the partial with respect to x. Of course, y is going to go exactly the same way, so I know that dz dy is also 2y over 4 minus 2z. Now I'm going to set up the contents of the radical in the formula for surface area. So I got to square both of these guys, add them together, and then add 1. So they have the same denominator. When I square and add dz dx and dz dy together, I get this. So if you notice, this denominator can be written as 4 times 2 minus z squared. And 2 minus z squared is the exact same thing as z minus 2 squared. So I'm replacing that expression with 4 minus x squared plus y squared. From the original sphere equation. And that's going to get me this integrand entirely in terms of x and y, which is going to be better because I have to convert this to polar coordinates. So in particular, I see a bunch of x squared plus y squareds, which is easily converted over to r squared when I go to polar coordinates. Okay, so I'm just cleaning this up a little bit. I'm going to get common denominators to add these two terms together. Which will end up looking like that, and I'm ready to carry it to the integrand now. Okay, so let's set up this polar double integral. I've described my region in terms of this, this disk. That's an easy polar rectangle. Theta goes between 0 and 2 pi, and r goes between 0 and root 3. That's the radius of that circle. So I put those in the appropriate places in the double integral, and now I fill out the integrand. So I'm going to have square root of this expression, which was the formula converted to polar coordinates. And then remember, when you're doing polar integrals, your dA unit is r dr d theta. I can do u substitution on this thing because I see an r squared expression under the radical in the denominator, and I have an extra r factor up top. So that's going to set that. That's perfectly set up for u substitution. So if I let u equal 4 minus r squared, then du is going to be negative 2r dr. So changing the limits of integration over and then incorporating the extra negative from du, I get the following double integral, which now I can go ahead and solve. So antiderivative of negative u to the negative half is negative 2u to the 1/2. Plug in 4 and 1, and then complete the integral out like this. So I'm going to go ahead and complete this and get myself an answer. I can use technology to verify that this was the right thing. I actually know that the internet will tell me the formula for the area of a spherical cap. So I think I'll do that instead. If I just Google spherical cap, I can get the volume and area in terms of some dimensions of the sphere. So I'm going to copy that over here so that you see and just figure out what the values are for this particular problem. So this was a sphere of radius 2, and the h part, the height of the cap, was the distance between z equals 3 and z equals 4. So the height there is 1. So I'm getting an area of 4 pi either way, from the longhand integral that I worked out and from Wikipedia.